All right, so we're getting into what all this statistics has been building to. And there's two things. One is confidence intervals, and the other is hypothesis testing. So confidence intervals, we're probably going to really just get mean. If we have time, we'll look at other things, but it's really just a way to make a good estimate about what you expect your population to mean to be. And it's built around the idea is that we can't just pick one value as an estimate, but we're going to pick a range of values that are going to be an estimate. So it gives us a little wiggle room. But that's why it's an interval. We need to build a few things to get there. So all along, we've been saying that a sample mean is an estimate of your population mean. And that's still the case here. So a simple random sample of 100 fourth graders is selected to take part in a new experimental approach to teach a new teaching method for reading. Sorry. At the end of the program, students will be given a standardized reading test. So suppose that the mean score of the 100 children who were in the program is going to be right here. We get a mean score of all those children is 67.3. So now administrators want to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program. Like I said, this is one sample, but we know we could take other samples. We would get other possible means. And not all of them are going to be, necessarily 67.3. They're going to be, pretty much all over the place. So right now, the best estimate, however, that we have for the population mean is just that sample mean that we had found right here, the one sample we took. So for our sample, the population mean was 67.3, and we call that a point estimate. The idea of a point estimate is that this is like the spot that we're going to build around. So we are going to build around your point estimate. So even though we're building around our point estimate, like I said, there is a possibility that we get other means for samples like 70, 52, maybe, and that there's going to be a variety that we have. And it's kind of a question, it's like, which one of these do I pick to say is my point estimate? So for now, we just pick the one that we have, but those other ones are something to be out there that is something that we do have to consider. So basically what we know is that our population mean is going to do a lot of wiggling, not necessarily wiggling around, but we're going to get a lot of estimates for it. We built something called that margin of error. So like I said, it's very unlikely that that mean of 67.3 is exactly equal to the population proportion. There's a lot of variety of other samples I can have, and not all of them can be correct. So in order to estimate, for our estimate to be useful, we have to describe how close it is to being likely. So we expect that it's likely, but how likely is it close to that real population mean? So for example, we think it could be off by, let's say, maybe 10 points. So we would estimate that the actual interval that we expect to find your population mean to be in would be from here to here. So 57.3 to 77.3. Another way we can write that is that we would just say 67.3 plus or minus 10. This plus or minus 10 here that we add on, so like I said, this part's your point estimate. And all it is just a sample mean. And this right here is what we call the margin of error. And the whole point of the margin of error is it builds me a little bit of wiggle room around that point estimate to kind of try to capture what is really that population mean. Because like we said, we're pretty sure the population mean isn't 67.3, but we assume that it's fairly close because that is the whole idea of doing random samples and collecting means, is that the majority of the time, they should be fairly close to what the true means are. Okay. This interval that we make right here, So when we add and subtract that margin of error, this is what we actually are going to call your confidence interval. So all a confidence interval really is just a prediction. It's just a range of values that are a prediction. It's a range of values that we predict the population mean to exist in. Like I said, we expect that the population mean is somewhere in there. It could be anywhere. Maybe it's right here at the very edge. Maybe it's not. Maybe it's right here, like almost exactly in the center. But we expect that somewhere in this range, we expect to find that population mean. So the next question to that really is going to be like, how good of an estimate is this? Then it gets to something we'll consider our level of confidence. So suppose we require a certain level of confidence. Like I can just pick any old margin of error and just say, okay, this is my range. Like what if I said, well, my margin of error is plus or minus, let's say 60. That seems a little extreme. That's not even close to capturing a population mean. I mean, that's not even close to narrowing in on a population mean, but it gives me a good range. And maybe with 60, there's 100% chance I am going, or let's put that again, I'm 100% confident I'm going to have that actual population mean in there. Um, but if I could pick something else, like let's say 20, 20 gives me a smaller range to look at. So maybe in this range, I'm, maybe like 99% confident I'm going to capture it. I could even make it even smaller and say maybe plus or minus 5. And maybe there I'm like 85% confident that I'm going to capture it. So this level of confidence is saying how, it's not really a probability, but saying how confident I am that I've made a range that really contains my population mean. So say our level of confidence is 95%, that the interval contains the population mean would be a confidence level. So the real question is, what should the margin of error be in order to have a 95% level of confidence or an 80% level of confidence or 100% level of confidence? We're never going to do 100 though. Like I said, different levels of confidence. So what should that margin of error be that makes sure that my population mean is in that interval? So level of confidence is really just how sure I am that I captured it. The level of confidence is how sure I am. I need to get rid of that. I don't need that little mark there. This is how sure I am that the confidence interval is how sure I am that confidence interval contains mu or my population mean. And as you're seeing there, as I was talking about my different levels of confidence, I was changing that margin of error. So if I have a very large margin of error, I'm much more confident that I'm going to capture that population mean. If I have a smaller error, I'm much less confident that I'm going to capture that population mean. What we're going to talk about eventually is, or here soon, is how do I calculate that margin of error? Because I need to have that margin error match the percentage of confidence that I have. So the margin of error is any level of any level of confidence can be found using a sampling distribution. Because when we're talking about percentages, we're usually talking about looking at our probability distributions. So this would be a probability distribution of my sample means. So that's what I'd have to use. We begin by finding a margin of error of 95% confidence, sorry, we begin by finding the margin of error for a 95% confidence level, and then we generalize the method. So we're going to talk about just finding one and then how we find others. Just a little quick part, and we're going to go through this again, but just a general idea what a confidence level means is we're talking about something in percentages, but we're not actually talking about a probability. So a confidence level is how certain we are that our confidence interval for the mean will contain the population mean. So if we say we have a 95% level of confidence, that means that 95% of all 90% of all confidence intervals, that's a typo though. So every time I get a point estimate, I'm going to build a new confidence interval. So that means 95% of all confidence intervals built around every possible point estimate that exists will contain the population mean. So it's not truly a probability. It's just something that I know because the way I'm going to build it, I'm building this in a way that I know that 95% of all the confidence intervals that I can make around every possible point estimate that exists are going to actually capture that population mean. And that's what we see over here. So all these circles here, these blue dots, they're just different point estimates. Because like I said, there are several samples I can take and I can get a lot of different point estimates. Most of them are pretty close to this dotted orange line, which is going to be my mean or my population mean. So like I said, most of these dots are pretty close to it, but occasionally you get one that's really far away. And if you went through and you counted this, I think it was, there's 45 of these lines, I believe, and 43 of them actually capture your population mean, which is going to be 43 divided by 45 is really, really close. It's actually 95.5%. But that's the idea is that I expect pretty much close to 95% of those intervals are going to capture that population mean. And that's what we're trying to do here is we're just trying to make a good guess of where that population mean exists. Most of these are good cases. And then we have this one. This one's going to completely miss what the population mean is. But generally it should happen. Okay, so back to finding this margin of error. So if I want to find my margin of error, and like I said, we have, say, 95% level of confidence. And remember point estimates. Or X bars. This means that this is a distribution. Let's use a different color. Of all my different X bars. So I'm looking at a distribution of all my possible means. And because we have a 95% level of confidence, we want to make sure that 95% of my means, my point estimates are good point estimates. So we're really trying to make sure that 95% of point estimates are close to mu. This is totally the idea here. And remember, this is mu. That would be mu for a distribution. It should be exactly in the center. So what we're saying here is that we want to have 95% of these values to be really, really close to mu. So we make a distribution where this area here is going to represent 95% in the center. So we need to figure out what Z1 and Z2 are. So if you use your Z table or you use your calculator, what you're going to find here is that Z1 for this 95% in the center would be negative 1.96 and Z2 would be a positive 1.96. So this is Z-score that we get when we're looking at this, taking out this 95% in the center. This is what we call a critical value. And where that name comes from is what we're going to start getting into is there's going to be a point where we really start talking about what happens in these tails. So if we're talking about those areas and the tails, the border between the area and the tails and the rest of the distribution is your critical value, because the area in the tail is what we call a critical area. That's going to have more significance when we talk about hypothesis testing than it does here. But that is where we get that name of a critical value, because it's the boundary between the rest of your distribution and your critical regions. So to remember z-scores, since we are estimating a population mean with a confidence interval, we must use a sampling distribution of sample means. This means we are finding z-scores of sample means. So those z-scores that I'm finding are going to be attached to this kind of z-score. So we have to have x bar minus mu subscript x bar divided by sigma subscript x bar. Or another way of saying this, if you remember, that the mean of all my means is the same as the population mean. The standard deviation of all my means is going to be the population standard deviation divided by the sample size, or the square root of the sample size. So another way of saying this is that the z-scores we're looking at are going to be z-scores for x bar minus the population mean divided by sigma, which is then divided by the square root of n. So this will kind of help us sort of build what we're going to be doing when we build these confidence intervals. What is really our margin of error? So this is highly dependent on all that information about the z-scores and probability distributions. So recall that we needed to calculate the value of the variable we need to calculate the value of a variable x. And we were given only a z-score. The formula was x is equal to mu plus z times sigma. Since we were calculating the value of a sample mean, essentially, so we're trying to calculate a mean, then that changes to this. So now your mean is going to be equal to your mean of your population plus or minus your z-score times your standard deviation. Or another way you can kind of look at it is that your mean can be approximated by taking x bar and subtracting z times your standard deviation. So it's a variation of this formula that we're going to be using. But remember, the z-scores we're using are going to be positive or negative z-scores. We actually have a positive and negative z, so we're really looking at mu is going to be x. Now we have to have a plus or minus because z could be positive and z could be negative, so it's a plus or minus z times sigma divided by the square root of n. So we're going to see this formula here in just a moment, but just to give you an idea of where it came from. Okay, so just something to mention here that, like I said, we kind of overlooked it. We've been overlooking it here and there, but this only works if because remember, we're looking at a distribution of means, we have to apply central limit theorem. And central limit theorem is going to tell us that as long as we have a sample size over 30, then the sampling distribution of x bars is approximately normal. And we are going to have that mean of mu and that standard deviation of sigma subscript x bar. And because our sampling distribution of x bar is normal, 95% of all sample means will lie within 1.96 standard deviations of the mean, like we said should happen. But we do need to make sure that our sampling distribution, our distribution of x bars, is actually normal, or your confidence interval actually makes no sense. So distribution of x bar have to be normal. Not in that confidence interval. It's actually kind of gibberish. Because then if we have a distribution that's not normal, if you remember, then all my predictions are, I basically mean nothing. I don't have good predictions. Okay. So if you remember, I gave you this formula earlier. Mu is equal to x bar plus or minus z times sigma divided by the square root of n. Okay. So a margin of error, 95% confidence. So before, like I said, 95% of my data should be between a z-score of -1 point, or 95% of my x bars are between a z-score of -1.96 and positive 1.96. That means that mu, what we think it should be, or more like backwards this, all our x bars, because this is my mean, all my x bars should be between my mu plus 1.96 times the standard deviation, because that'll tell me what this value is out here. This is going to give me another mean, essentially. And then on this side, we'll have mu minus 1.96 times the standard deviation, which gives me that there. Just using a little bit of algebra, what we're going to get is that mu is actually going to be between, instead of the bar being in between, mu is going to be between x bar minus 1.96 sigma sub x bar and x bar plus 1.96 sigma sub x bar. So no, it's pretty much the same thing. So really what we're looking at is just a modified, just modifying our z-score a little bit. So with 95% confidence, the population mean mu is contained, even though we don't know what x bar and sigma are, is contained between x bar plus or minus 1.96 times sigma sub x bar. So this part right here, that's the part that's your margin of error. Right there. So this part that's added on to your point estimate, that is your margin of error. So margin of error is just your critical value. So it's that z-score times the standard error, which is your standard deviation. So it's really going to be the z times sigma divided by the square root of n. Okay, so try can make this a little more concise. Point estimate, the mean of a sample x bar. Your critical value is the z for the confidence level. Your standard error is also considered your standard deviation of sample means. And that's going to be that sigma sub x bar, which is equal to sigma divided by the square root of n. So like I said, your margin of error is going to be your critical value times your standard error. So it's going to be z-score times the standard error or your standard deviation of sample means, or z times the population standard deviation divided by the square root of the sample size.